This video is about memorizing sine and cosine values for important angles. What are the important angles? In the first quadrant, we have 0, then we have pi sixth, then pi fourth. As you see, the denominator is decreasing, so the value of the entire fraction is increasing. So if I put them all in increasing order, then you might have memorized it already, but here's a very cool way of memorizing it. Sine of these angles is going to be, for 0, it would be square root of 0 over 2. For pi over 6, square root of 1 over 2. For pi over 4, square root of 2 over 2. For pi over 3rd is square root of 3 over 2. For pi over 2, square root of 4 over 2. 3 of these items simplify. These two do not simplify, but that one simplifies to 1/2. This one simplifies to 0. This one simplifies to 1. And so how do I find a cosine? Whatever value you found, we start from the very last one. Very last one goes over here. This one is the next. That one is next, and then next, and next. So I recommend for a while, if you keep forgetting the values until it's completely part of your routine, you want to draw this table and put in the angles 0, pi 6, pi 4th, pi 3rd, and pi half in that order. Then start with the square root of, if you notice, square root of 0, square root of 1, square root of 2, square root of 3, square root of 4, all on the denominator 2, and then simplify it to get the sine, and then to flip the order to get the cosine theta for those angles. That was just the first quadrant. So I can put the first quadrant in, and let's say this is pi 3rd. I'm not putting the angle over here because there will be lots of angles. So I have, this one is pi 6, I'm sorry. And then in the middle, in here, we have pi 4th, then we have pi 3rd. And so x and y for pi 6th, x is square root of 3 over 2, and y is 1/2. So I'm putting it over here, square root of 3 over 2, and 1/2. For pi 4th, both of them are square root of 2 over 2. For pi 3rd, I'm over here, it's 1/2 and square root of 3 over 2. Now we had the discussion of I can find angles that are in some sort of symmetry with these. Their terminal side is in some sort of symmetry with these on the other quadrants, and then calculate their sine and cosine using which quadrant they're happening at. So how do I do that? Let's see. For pi 6th, here is the These values are in symmetry with pi sixth, and so let's calculate this. This one is going to be on a piece of scratch paper. That one is going to be pi minus pi sixth, which is 5 pi sixth. This one is 5 pi sixth. This one is pi plus pi sixth. That would be a common denominator again, 7 pi sixth. And this one is 2 pi minus pi sixth. And that would be 11 pi sixth. Now, 5 pi sixth is in the second quadrant. Therefore, the x value should be negative. The y value should be positive. So I use this value to find the x and y value for this one. Minus 3 square root of 3 over 2 and positive 1/2. Therefore, this is cosine of 5 pi sixth. This is sine of 5 pi sixth. For 7 pi sixth, both values should be negative in the third quadrant. Therefore, I'm writing the ordered pair this way. For 11 pi sixth, x value is positive, y value is negative. Therefore, I have to write it as x value positive, y value negative. Again, cosine of 11 pi sixth is square root of 3 over 2, and sine of 11 pi over sixth is negative 1 over 2. Now, let's do this for pi fourth. For pi fourth, let's calculate, that was an error. Pi fourth should be somewhere in the middle of each quadrant. Okay, and so for pi fourth, calculating this one gives me pi minus pi fourth because there is a symmetry over here, and so on scratch paper I calculate pi minus pi fourth. Common denominator, 4 pi minus pi over 4 is 3 pi fourth, so 3 pi fourth. Over here it's pi plus pi fourth, so it's 5 pi fourth. Over here, this one in the fourth quadrant is 2 pi minus pi fourth, which is 2 times 4, 8, minus 1, 7 pi fourth. And then the values for x and y, here x should be negative and y should be positive. Therefore, I'm using this, negative for x, positive for y. So cosine of 3 pi fourth is negative square root of 2 over 2, and sine of pi fourth is square root of 2 over 2. Now for 5 pi fourth, both sine and cosine have to be negative. Both x and y are negative. Here for 7 pi fourth, the x values were positive, y value is negative. So cosine is positive and sine is negative. I'm separating the scratch work. and separating the scratch work. So out of the reference angles from 0 to pi half, the famous reference angles, we've done pi 6 and pi 4, and what's remaining is pi 3. So let's see, pi 3, and then we draw the ones that are symmetric with pi 3. And then on the scratch work, first calculating this is pi minus pi 3, which is 2 pi 3. And then the next one is over here, that's pi plus pi 3, which is 4 pi 3. And then the last one over here is 2 pi minus pi 3, which is 5 pi 3. Now the x and y value of the terminal point, in here pi 3 was associated with 1/2 and square root of 3 over 2. Now over here the x value has to be negative, y value positive, so cosine of 2 pi 3 is negative 1/2, and sine of 2 pi 3 is square root of 3 over 2. Over here, both sine and cosine should be negative. So it's negative square root of 1 over 2 is the cosine of 4 pi 3, and negative square root of 3 over 2 is the sine of 4 pi 3. Over here, x value should be positive, y value should be negative. So cosine is positive, sine is negative. Now, the next question is, how about these endpoints? Okay, this one is angle 0, and that is 1 and 0, so cosine is 1, sine is 0. This one is angle pi half, and 0 and 1, so cosine 0, sine 1. In here, pi, and negative 1 and 0, so cosine pi is 0, sine of pi is cosine pi is negative 1, sine of pi is 0. I'm sorry about that. And so 3 pi half, and then I get 0 and negative 1. That is cosine of 3 pi half is 0, sine of 3 pi half is negative 1. Okay, so this scratch work took a while for me to do, and I cannot avoid the unit circle, but can I avoid the scratch work? First of all, every time I'm looking at angles that are related to the famous angles in the first quadrant, I see there is a relationship. Over here, I see denominator 3 related to denominator 3, denominator 3, and denominator 3. Denominator 4 is related to denominator 4, denominator 4 is related to that one, and denominator 4 is related to that one. Again, with the denominator 6 as well. Can I make another rule and just is there any easy way to putting all these famous angles around the unit circle, and then by knowing the table I will know everything else out of that? And so yes, there is. Let's start with pi 6. Pi 6 is 1 pi 6. if I start counting the numerator from 1 all the way to 6, I should be able to get a pattern. Let's see. 1 pi 6 is the reference angle. 2 pi 6, 2 and 6 simplify, right? 2 pi 6, 2 pi 6, 2 and 6 simplify, so it doesn't count. 3 pi 6, 3 and 6 simplify, so it doesn't count. 4 pi 6, 4 and 6 simplify, so it doesn't count. 5 pi 6 are the first time that the numerator and denominator, the integer in the numerator and denominator are mutually prime. They don't have any common factor. So this one's okay. That one goes in there. That's the first one after the reference angle, goes to the second quadrant. And the next one after that is going to be 6 pi 6. 6 and 6 simplify. The next one is 7 pi 6. 7 and 6 are mutually prime, therefore this one counts, goes over here. Then we will have, then after that we'll have 8 pi 6, that doesn't count, 9 pi 6, that doesn't count. Then I will have 10 pi 6. Let me erase this part and rewrite this. So 7 pi 6, 8 pi 6, 9 pi 6. These are all simplifiable. 10 pi 6 again. 11 pi 6 is the next one. So 5 pi 6 is the first one. After reference angle goes over here. Then 7 pi 6 goes over here. Then 11 pi 6 goes over there. And I got everything that is related to the reference angle, pi over 6. Now, I want to do this with the 3 pi 4. So what is related to reference angle 3 pi 4, 1 pi 4? Starting with 1 pi 4, that's the angle itself. Then I get 2 pi 4, 2 and 4 simplify, doesn't count. 3 pi 4 counts. 4 pi 4 simplifies, doesn't count. 5 pi 4 counts. 6 pi 4 simplifies, doesn't count. 7 pi 4 counts again. So you see that over here I have 3 pi 4, that's the first one in the second quadrant. Then I have 5 pi 4 in the third quadrant and 7 pi 4 in the fourth quadrant. How about pi third? So when you start with the pi third, so with the pi third is a reference angle. 2 pi third doesn't simplify, that's fine. 3 pi third, 3 and 3 simplify, it's not. 4 pi third doesn't simplify, counts. 5 pi third counts as well because it doesn't simplify. So with this reference angle, I will have that one on over here, this one over there, and this one over here. This method is much faster than the scratch paper for many of you, so I do recommend that. And then the next thing that you want to do is to put all the angles on a unit circle. Use this table that is easily memorized to find all the values for sine and cosine. And that's how we memorize sine and cosine for important angles. So we want to discuss angles in radian, arc length, area of a sector, and angular speed. When we were defining the radian value for an angle, we discussed that it's related to the length of the arc on a unit circle, that theta is facing. This is a fine definition, except that we have to have in mind that this length is unitless, and we cannot use any units for that one. Generally, the definition, the actual definition of the angles in radian comes from the same logic, but the formula that the logic brings to you. So usually when we're discussing the angles in radian, we're defining it by pi times the angle in degrees divided by 180 degrees. And the radian value is unitless again. So the definition that we used, or how we discussed it in the beginning, just gives you the logic behind how it works. Now we want to discuss the arc length and area of a sector. Let's say that we're not in unit circle anymore. So here we're still in unit circle, or could be outside the unit circle, but in any way the formula follows that way. Here R, and it could be anything, it could be 1 or it could be any other value. And I want to see if in this circle the arc length that is facing angle theta. How do I compute that? If you go back to the unit circle and sort of the logical definition, not the formal definition, but the logical definition that we defined, we discussed that this arc length is is equal to theta. Now, in here, using that same logic, since the radius went from 1 to r, everything has to blow up or shrink by r. Therefore, the arc length should be r times theta. That's one way of discussing this. The other way of discussing this, so this is method number 2 of driving the same formula, basically, is that the arc length that theta is facing to the entire circumference of so the arc length, the ratio of the arc length divided by the entire circumference of the circle, which we know is 2 pi r, is equal to theta divided by 2 pi. So theta divided by 2 pi, that's the ratio of theta over 2 pi is the same ratio as the arc length to the entire circumference. That's another logical way of driving the same formula. And then the 2 and 2 simplify, pi and pi simplify, so you end up with arc length equal to r theta. So that was the method 1 using that logic, and this is the method 1 using the logic of what's the ratio between them. In here, we're trying to figure out the area of the sector. So the area of the sector that theta is basically it's like a slice of a pizza. So the area of that slice of the pizza, where the angle of that slice is theta, what would that be? And this one again, we use the second logical method of driving the formula this time. And this is theta, the ratio of theta to the entire, the area to the entire circle is the same as the theta to entire full rotation. So theta over full rotation, this ratio, full rotation is 2 pi, should be equal to the area of the sector divided by the area of the entire circle, which is pi r squared. Now we want to simplify everything. Here pi and pi simplify, and then I get area of the sector is theta times r squared divided by 2. Theta r squared divided by 2. So this is the discussion of the angle, the arc length, and area of a sector. The next thing is the angular speed. What is angular speed? Angular speed is the, and we show it with omega, is the angle. This is the average angular speed is equal to the angle that has been covered divided by the time that it was covered in. So omega is equal to theta divided by t. The next thing is how can I relate this to the actual speed? Remember, when you're trying to go in a circle, the distance you're traveling is the arc length. So basically, v is equal to the arc length divided by t. That's the average velocity. And v is going to be, what is arc length? Arc length is going to be r times theta divided by t. And I'm separating r. I'm bringing r outside the fraction, so it's equal to r times omega, or r times the angular speed. Those formulas are useful in your physics courses. And we're done with this section. So let's discuss in this video the other trigonometric functions. Tangent, cotangent, secant, and cosecant. What is tangent? Tangent of t, we show it with tan, big parentheses, because tangent is a function, as was sine and cosine of t, is equal to 1, sorry, it's equal to y over x, wherever x is not 0. So it's only defined when x is not 0. Now, the other way to express this, y was the sine of t, big parentheses, then x was cosine of t. Again, in this definition, you have to say where cosine of t is not equal to 0. What about cotangent of t? Cotangent, we show it with COT. Cotangent of t is x over y. That's the reciprocal of that one, as is defined when y is not 0. Therefore, I can show it as cotangent of t is equal to cosine of t divided by sine of t. This is defined when sine of t not equal to 0. Again, tangent of t is equal to 1 over cotangent of t. They're reciprocal of each other. Or cotangent of t is equal to 1 over tangent of t. The next one is the secant t. So we show it with SEC, big parentheses, because it's a function, and t inside. T is the variable, and that is equal to 1 over x, when x is not 0. What was x? X was the cosine. Cosine of t, when cosine of t is not 0. And the last one is the cosecant t. Cosecant is CSC. T is 1 over y, where y is not equal to 0. Also, it's 1 over sine of t, when sine of t not equal to 0. These are the quotient formulas and the quotient and trig functions. And it's important and where the denominator is 0 for each one of them, you will have a vertical asymptote at those points. So you have to evaluate where cosine of t is equal to 0, sine of t is equal to 0 for cosecant, and so on and so forth over there, and there will be vertical asymptotes. The other thing that I want to mention in here is these formulas are important. That's the first thing. Those are generally how I memorize the tangent, cotangent, secant, and cosecant formula, rather than knowing y over x or x over y or so on and so forth. Tangent is the way I memorize it. I remember tangent. Tangent is sine of the angle divided by cosine of the angle. Then I remember that secant is on the same boat as tangent, and therefore the denominator of secant should be the same as the denominator of tangent. And then the cofunctions, cotangent and cosecant, have to have the same denominator, and cotangent is the cofunction of tangent, so it's the reciprocal of that one. And that's how I memorize all of them. And there's one more thing that I want to mention. At some point we learned that sine and cosine functions are periodic. That is, you can find a value. Periodic means there is a value, and usually we find the smallest value, p, such that if I add it to x, to the input, the output does not change. And for sine and cosine, this p is equal to 2 pi for sine of x and cosine of x. Now, for tangent and cotangent, the period is going to be pi. So period, or what makes it periodic, is equal to pi. And that's it for this video, and until the next one. The purpose of this video is to discuss trigonometry of right triangles. So far we discussed the values of trigonometric functions over or inside the unit circle, or somehow related to unit circle. Now we're discussing how to find the values of trigonometric functions using triangles or similar triangles. And so the first thing is the notation. If you have a right triangle like this, and this is the right angle, and you want to find the trigonometric functions for theta, and then theta would being this angle, then notice that the side that is facing the right triangle, the biggest side, is going to be called hypotenuse. We also show it with an H. The side that is adjacent next to, beside the hypotenuse, that is adjacent to theta, is called adjacent. And the side that is facing theta is going to be called opposite. Now, trigonometric functions for this are as follows. Sine of theta is equal to opposite over hypotenuse. Opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. Tangent theta is equal to opposite over adjacent. Cotangent theta is equal to adjacent over opposite. And people have ways of memorizing this. This is SOH. SOH. This one is CAH. This one is TOA. This one is CAO. So what is that good for? First of all, one thing that I want you to notice is that since any right triangle that has an angle equal to the theta is going to be similar to this triangle, it doesn't matter, it's this one, the finding these ratios is not related to the size of the triangle, because they're all similar, and these are just ratios of two sides of the two similar triangles. The two corresponding sides are going to be the same anyway. The next thing is I'd like to do a few examples on the that are related to these formulas. Let's say this is the example one, and here I'm planning to find the values, the trigonometric values for t. So plan is to find sine of t, cosine of t, tan of t, cotan of t. Now, looking at the values, the side that is adjacent to t is this one. This one is the hypotenuse, and this one is the opposite. I do have two of the three sides, and the other part that the side that I don't know, I can use the Pythagorean theorem to solve for. So the first thing for this question is to use the Pythagorean theorem. Use Pythagorean. And that is 15 to power 2 is equal to 12 to power 2 plus opposite to power 2. And when you solve, it's 225 equal to 144 plus O squared. And then that gives you O squared is equal to 81. So O is equal to 9. So this one equal to 9. Now, and sine of t is supposed to be opposite over hypotenuse. Opposite is 9. Divided by hypotenuse, which is 15. You can simplify that to 3 over 5. Now, cosine of t is adjacent over hypotenuse. That's 12 divided by 15. That is 4 divided by 5. Tangent of t is equal to tangent of t and cotangent of t. Tangent of t is equal to opposite over adjacent. That is 9 over 12, which is 3/4. Then cotangent of t is going to be equal to the adjacent divided by opposite, and that's 4 over 3. Or I could have used the quotient identities to figure this two out. I can find the secant of t by, and I know secant of t has to have the same denominator as tangent of t, so it's 1 over cosine. So secant of t is 5 over 4. And cosecant t is equal to the again, another quotient identity is 5 over 3. So the next example is to find the trigonometric values for s in the same triangle. This time, the side next to s beside the hypotenuse is this side, and this one is the opposite. And a is, again, by Pythagorean theorem, is 9. Now, when I'm finding values, again, sine of s is going to be, this time, the opposite is 12 divided by hypotenuse. It's going to be 4/5. The cosine of s is going to be the adjacent divided by hypotenuse. That's the 3/5. Secant of s is just the inverse of that one by the identity, and inverse of this one by the identity. Tangent of s is the opposite over adjacent, which is 12 divided by 9, and that is 4/3. Cotangent of s is the inverse of that. And you can compare these values to these values. Here, the sine and cosine of t, they switched when they became for sine of s and cosine of s. So basically, sine of s is equal to the cosine of t, which is the cofunction of sine for t, and then the other way around. And also for tan and for cotan and for secant and cosecant. The values here are the values for s are equal to the cofunctions of them in t. And that's actually an identity, and it's always true for the two angles that make 90 degrees or pi half. The last questions that I want to do is this one. Example. Find the values for theta over here. In here again I have the opposite is given, opposite and adjacent are given. Use another Pythagorean theorem. And that is 10 to power 2 plus 24 to power 2 is equal to hypotenuse to power 2. 10 to power 2 is 100, and 24 to power 2 is 576. So h to power 2 is equal to 676. That is, h is going to be equal to 26. Okay. Now, sine of theta is the opposite over the hypotenuse. 24 divided by 13, which is 12 divided by 26, which is 12 divided by 13. Cosine theta is 10 divided by 26. And tan theta is 12 divided by 13. Cotan theta is equal to 13 divided by 12. So these examples had one thing in common. Some of the sides were given, and we found the trigonometric functions for theta. And the other way around, the other type of examples is that when the trigonometric function or the angles are given and one of the sides is given, then you can find the other sides of the triangle. And we need some practice over those as well.